As the James Webb Space Telescope continues its cosmic odyssey, the images of distant galaxies and potential supermassive black holes stand as testaments to humanity's insatiable curiosity. The telescope's transformative capabilities not only captivate our imagination, but also provide invaluable data for scientists worldwide. These awe-inspiring images serve as a reminder that the universe is a vast, dynamic tapestry waiting to be unveiled, and the James Webb Space Telescope is our window to the cosmic wonders beyond. In the beginning, there was a bang, Big Bang, if you will. This massive explosion created the universe and filled it with the seeds of all the matter and energy currently present. But with that kind of turbo kickstart, growth isn't something that ends after the initial blast. The universe continues to expand, even accelerating as it goes, at a rate referred to as the Hubble constant. The Hubble constant is an incredibly important number to pin down in the field of cosmology, but it's not an easy one to suss out. In fact, it's so difficult to divine that the Hubble tension caused by our inability to land on a single number has become arguably as famous as the Hubble constant itself. And recent results from the James Webb Space Telescope have just re-cemented this tension as a very real problem to overcome. If a researcher wants to estimate the Hubble constant, they have two main avenues. There are others, of course, but the two most common are Cepheid variables and the cosmic microwave background. The cosmic microwave background is the leftover radiation still permeating the universe from the Big Bang. Using the cosmic microwave background is often likened by researchers to using a baby picture to predict what someone will look like as an adult. To some extent, knowledge about the universe's infancy should allow researchers to make predictions about its current state. Researchers have long used it to make inferences about the very beginnings of our universe, and have used it to predict what the Hubble constant should be. Fairly recent cosmic microwave background calculations set the Hubble constant at around 68 kilometers per second per megaparsec. But the thing about theory is that you need to test it, and when the Hubble telescope launched, it became possible to do just that. Free of the constraints of ground-based telescopes clouded by atmosphere, the Hubble telescope was able to take extremely accurate distance measurements of far-off objects. And that's where Cepheid variables come in. Cepheid variables are a type of pulsating star that falls into a category of objects called standard candles. Objects that have a measurable and consistent brightness, allowing us to fairly straightforwardly measure how far away they are. Measuring distances isn't easy in space, but it's crucial to being able to measure expansion. As convenient as it would be to stop there, there's one more step to the Cepheid method. Once their brightnesses have been divined and we know how bright a Cepheid is that blinks at a certain rate, we use those brightnesses to calculate the brightnesses of nearby supernovae. Then, using a quality called redshift, we use those supernovae to calculate the brightnesses of other supernovae that are even farther away. Because they're much brighter, we can see supernovae at much greater distances than we can see Cepheids. And because you can see the expansion of the universe better the further away you look, we look to the far-off supernovae for the ultimate calculation. This chain of brightnesses is referred to as a distance ladder. And you can't move to one rung without first calculating all the ones that come before. Over time, the Hubble telescope clocked distances for several Cepheid variables, the first rung on that distance ladder, which in turn allowed researchers to make an experimental measurement of the Hubble constant. But instead of agreeing with the prediction, it came out totally different: 73 kilometers per second per megaparsec. When experiment and theory diverge, it can mean one of two things: either your measurement is wrong or your theory is wrong. And that, in a nutshell, is the Hubble tension. Which is wrong, the theory or the experiment? That is where James Webb can help. By observing in the infrared spectrum, it will be able to look straight through pesky clouds of space dust that all too often interfere with local astronomers' measurements. The Hubble Space Telescope, the previous tool of choice for local astronomers, has far more modest infrared capabilities. Its infrared measurements come at the expense of lower image quality. But James Webb can do both. Observe in infrared and maintain high-resolution imaging. Crisper, dust-free images. That Webb promise. The telescope is such a technological improvement that scientists expect its unprecedented infrared measurements might at last bridge a growing rift between astronomers over how fast the universe is expanding. And in a remarkable observation, the telescope took images of the same stars as the Hubble telescope and calculated a very similar Hubble constant. Although the Planck number disagrees from Hubble and James Webb number by less than 10%, the discrepancy in the measurements implies that there's something terribly wrong with our understanding of the universe. Unless an error turns up in one of the measurements, it will take strange new physics to explain the tension. As cosmologist Adam Rees of Johns Hopkins University, papers in the literature over the last 10 years have invoked anything from weird dark matter to weird dark energy, to another exotic particle, to a magnetic field in the early universe, to a new field, all kinds of things. Some of these explanations look semi-successful, some of them look like failures, some of them would cause other problems. Developing a theory that might resolve the tension is still very much in the skunk works or extremely speculative stage of trying to understand what the tension could mean. Like the Hubble telescope, astronomers using James Webb calculate the Hubble constant by observing flashing stars known as Cepheid variables. As told, combining distance and speed observations of Cepheid stars leads to a measure of the expansion of the universe. But Cepheid variable stars tend to sit deep inside galaxies, surrounded by crowds of other stars. That can make it difficult to get good measurements of the Cepheid speeds and locations. One simple resolution for the Hubble tension could have been that the Hubble telescope measurements were simply off. Enter James Webb, which can peer through the stellar crowds to clearly make out the color and brightness of Cepheid variables. The higher resolution Webb images provide data with dramatically lower uncertainties and reduced confusion with nearby stars than the Hubble telescope could manage. The result? The Hubble telescope measurements have been right all along. This study alone isn't enough to convince astronomer Wendy Friedman of the University of Chicago. The two galaxies studied are comparatively close to us, on cosmic scales, with the farthest one about 75 million light-years away, she notes. The relative proximity makes it easier to pick out the Cepheids from the stellar crowds. Friedman suspects it will be harder to distinguish Cepheids from the crowds of surrounding stars in more distant galaxies, even with James Webb. If so, Rees's confirmation of the higher Hubble constant may crumble with analysis of more distant Cepheids. Hints that the measurements might hold up at larger distances arose in S' presentation at a conference in Baltimore dedicated to the first year of James Webb science. Rees showed preliminary Cepheid data from 4 more galaxies. One of them is 140 million light-years away, among the most distant galaxies in the Hubble telescope Cepheid studies. Webb data from those stars also line up with the Hubble telescope measurements. Although still awaiting peer review, the images strongly suggest that James Webb has indeed overcome the uncertainties that resulted when light from Cepheids got mixed up with light from nearby stars in the lower-resolution Hubble telescope images. University of Cambridge astrophysicist George F. Stathiou, who was not involved in the study, is both convinced that Rees has gotten the measurements right and confounded by the implications. F. Stathiou is a member of the Planck satellite collaboration, which studied the oldest light in the universe, called the cosmic microwave background, and found the lower value for the expansion of the universe. The satellite's calculation is based on images of the patterns in light from the early universe. Together with the standard model of cosmology, The images show that the universe is expanding with a Hubble constant that's lower than James Webb measurement by about 5.6 kilometers per second per megaparsec. As it stands, there doesn't seem to be anything wrong with the Planck measurement of the Hubble constant or with Webb observations. The tension between the measurements points a finger at the standard model of cosmology as the problem. But the standard model also appears to be unimpeachable. It's withstood numerous other challenges without breaking down. The model came about in part due to the discovery of the accelerating expansion of the universe, which earned Rees and others a Nobel Prize in physics. The revelation was a key piece in shaping the model to include dark matter, dark energy, and other factors, making it the simplest theory that can accurately describe the universe. After all, we know that there's still more to learn. This is a crack or a surprise that doesn't fit. Put simply, there's a problem with the standard model. We can revise it, but we don't know how to revise it, which direction or in what way. But note that we also can't rule out the possibility of completely new physics. According to Friedman, if there's new physics, that'd be fun. We'd all like to see something new and interesting. Either way, I think it's going to be an exciting result, either confirming the standard model or showing that there's something still in the model that's missing. Regardless of the final result, scientists still expect James Webb to find it. A silver lining, astronomers observing the galaxy MRG M0138 with the James Webb Telescope have discovered a second type UI, a supernova in the distant galaxy. The first supernova was nicknamed Requiem. This second supernova has been called Encore. MRG M0138 is the most distant galaxy to be seen with two-type Ia supernovae, and in fact, that's very important for helping to solve what is possibly the greatest puzzle in cosmology right now. However, there's a catch. While most of the images of the two supernovas have appeared, one of the light paths is predicted to be much longer, based on models of the distribution of dark matter in the lensing cluster. Those phenolimages are not expected to appear until the mid to late 2030s. While the aging Hubble Space Telescope might not still be active in 2035, hopefully James Webb will still be. If it is, and if it can detect the appearance of the final images from Requiem and Encore, the measurement of the Hubble constant that they provide could help settle the matter of whether so-called Hubble tension is merely experimental error or a real phenomenon. Back on Earth, astronomers have long wondered how Earth became water-rich, bountiful with abyssal oceans, frigid glaciers, and rain that pours from the sky into lakes, rivers, and wetlands. Water, which is composed of the first and third most common elements in the universe, is a deceptively simple molecule to form. However, while the details of its delivery to rocky planets like our own may be essential for understanding life's cosmic prevalence, they remain mostly unknown. Water is a potent medium for the assembly of complex organic molecules and offers havens for the emergence and subsequent evolution of life as we know it. Deep within Earth, it ensures the lithic lubrication that keeps climate-stabilizing plate tectonics from grinding to a halt, another mechanism that just might be crucial for life. And when frozen as ice, it plays a key role in planet formation by providing the glue that helps young worlds grow. As such, scientists are anxious to better understand water's planetary peregrinations, the pathways it takes to transform planets from desiccated rocks into worlds as soaked as Earth. To gain more insight, astronomers are utilizing the James Webb Space Telescope to peer into protoplanetary disks, the swirls of gas and dust around young stars where planets are actively forming today. Although astronomers have glimpsed water within such disks before, their view has been hazy. For example, water vapor is visible to the Atacama Large Millimeter Submillimeter Array, or ALMA. In many respects, the most powerful radio observatory on Earth, but the facility largely cannot detect water ice. This blocks a protoplanetary disk's outer regions from ALMA's scrutiny. The array also cannot deeply probe the hot inner regions of disks where terrestrial bodies form. James Webb, on the other hand, was designed with such studies in mind and has, quite literally, opened the floodgates. The new Space Observatory is delivering unprecedented looks at how water passes from star-forming giant molecular clouds into protoplanetary disks and finally onto planets, with significant implications for astrobiology, including whether our own watery world is somehow special or commonplace. As Andrea Banzotti, a Texas State University astronomer studying protoplanetary disks, said, "With James Webb, it's like suddenly you try on new glasses and they give you a much sharper view." Water's cosmic odyssey began hundreds of millions of years after the Big Bang. That's when the first stars, which had furiously fused through their hydrogen store to churn out heavier elements, burst into supernovae that seeded the universe with oxygen. At this point, a single atom of oxygen could mingle with two hydrogen atoms to form a molecule of water, a molecule that could, in a cosmic cycle of creation and destruction, still be sundered anew by high-energy radiation from stars and other astrophysical sources. But sooner or later, undoubtedly billions of years later in some cases, such water found its way to the cold confines of molecular clouds, where another chaotic and violent chapter of its journey would begin. Molecular clouds are giant, chilly clumps of dust and frozen gas that contain abundant water ice and serve as cradles for stars and planets alike. When part of a cloud reaches some critical density, gravity causes that dense, roughly spherical region to collapse into a flattened, whirling protoplanetary disk with a nascent, glowing star at its center. Much of this process is obscured by dust and has proved almost impossible to probe, until James Webb. It took Webb's incredible sensitivity to enable us to catch the few photons that make it through and hence characterize the icy grains right before the onset of star and planet formation, says Karen Auberg, an astronomer at Harvard University. From there, the growing star feeds on material raining in from its enveloping disk, creating more light and heat, and potentially breaking apart the disk's water molecules to bake off moisture that would have otherwise flowed into worlds. If this process happens too efficiently, the result would be galaxies full of parched planetary systems, and we might well not be here, which is in no small part why most scientists suspect this can't be the case. Somehow, water must pass unscathed from placid molecular clouds through sizzling star-forming disks. In 2021, John Tobin, an astronomer at the National Radio Astronomy Observatory, and others used ALMA to observe V883 Orionis, a disk-wreathed protostar located 1,305 light-years from Earth that is only slightly more massive than our Sun but shines roughly 200 times brighter. The protostar's radiance heats up the frigid outer disk, transforming ice to water vapor that becomes a beacon for ALMA's radio vision. It was a lucky break. Tobin's team saw high ratios of semi-heavy water, in which the heavier hydrogen isotope deuterium substitutes for one of a water molecule's two standard, lighter hydrogen atoms. Because semi-heavy water can only form in cold temperatures, and not the high temperatures directly associated with star formation, its origins around V883. Orionis must date back to the molecular cloud itself, suggesting that the water had passed through the star formation process unchanged. Indeed, the ratio of semi-heavy water to normal water that Tobin and his colleagues observed perfectly matched the proportion observed in other molecular clouds. It also matched the ratio found in our solar system's comets, hinting at one way that water can reach rocky worlds. Astronomers currently think that terrestrial planets can gain water in 3 different ways. It could be that water is there from the start, cocooned within grains of dust that are the very building blocks of the planets themselves. Or perhaps the growing planets siphon water vapor directly from the gas in the primordial disk, allowing gravity to build a humid atmosphere around their rocky core. Or maybe, once the planets have formed, they guzzle water imported via leftover icy debris falling in from far-flung regions of the planetary system. Tobin's results suggest that this latter pathway plays a prominent role, but that water-delivering comets and meteorites do not work alone. Water on Earth has a slightly lower ratio of semi-heavy water to normal water than that found in comets, meaning that while much of our planet's water arrived from the outer solar system's icy hinterlands, some must have instead been exposed to high temperatures near the sun. Just what that exposure looks like, however, remains an open question. To find answers, Oberg wants to build a cosmic map, pinpointing the locations of water around these young protoplanetary disks to see where it is readily available to feed any forming worlds. Alma has already sketched a blurry image, and James Webb is beginning to fill in the gaps with spectacular detail. Last April, Sierra Grant, an astronomer at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany, and her colleagues used James Webb to observe water in a disk that had previously appeared dry, demonstrating the Space Observatory's remarkable capability to wring fresh insights even from well-studied systems. According to Grant, we are really in a new era with James Webb. It's remarkable that we could detect things that we couldn't detect before. Then last August, Julia Perotti, an astronomer from the Max Planck Institute for Astronomy in Heidelberg, Germany, and others detected water vapor in PDS 70, the sole protoplanetary disk yet known to harbor not one but two giant planets. Their presence likely means that terrestrial planets are also coalescing within the inner disk, at the precise location where astronomers have now found water. Previous observations had shown no water at all, which was unsurprising, given that water would be hard-pressed to survive the intense radiation so close to the star. Now, astronomers know that it can and that it may just glom onto the atmospheres of planets as they grow, as opposed to reaching dry planets via interplanetary visitors later on. As such, most terrestrial worlds across the cosmos might be born rich, with a wealth of water from the very start. That by itself could be a problem that could lead to worlds that are too water-rich. Scientists currently think that ocean worlds will struggle to create life, but a planet with pond-peppered continents will have much better luck. That's because many of the reactions thought crucial for prebiotic chemistry and the rise of complex chemical systems proceed much more efficiently in small, concentrated ponds than in expansive, diluted oceans. Moreover, minerals that erode from the continents will add crucial nutrients to the water. But to learn how often the universe builds terraqueous orbs like Earth, Oberg argues that we first need to understand young protoplanetary disks by completing that cosmic map, which shows not just the locations of water around these disks, but also how it flows from one locale to the next. Just how water pours from the icy outer region of the disk inward, however, has been unclear, especially in PDS 70, where there is a large gap between the outer and inner disks. Then last November, Banzati, Oberg, and others observed water vapor within the system's snowline, the transitional region, where shifting temperatures transform water from solid to liquid or gas. This confirmed a physical process whereby water migrates inward. 40 years ago, astronomers postulated that water ice in the outer disk would drift inward on sturdier solid material, dust grains and so-called icy pebbles that range in size from a few millimeters up to a few meters, until sublimating at the snowline in a great fog of water vapor. That's the precise signature that Banzati observed, and it has implications for PDS 70. Perotti suspects that this mechanism carried water inward before the gap formed between the outer and inner regions of the system's disk. Or it could be that water continues to migrate through the gap even now, albeit on much smaller, as yet unseen micron-sized icy dust. This dust, along with some water molecules, can act as a protective shield, keeping many water molecules from breaking apart. Oberg's cosmic map is thus becoming more and more detailed, with vast reservoirs found in many regions of protoplanetary disks, suggesting that water may well flow to rocky worlds in myriad ways. But still, astronomers do not know if one scenario has the upper hand. Thus, hope that James Webb's future observations should shed light on the dominant pathway, which might change depending on certain characteristics of the planetary system. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.